Okay, in this video tutorial I'm going to talk about water. Now that sounds like sort of an ominous or an interesting sort of topic, but if we're looking at biological molecules or things that are relevant to life, water is probably one of the most important. Alright, so let's start with this question. Why are the properties of water so essential to life? And in fact, we can ask this question a couple of different ways too. Why is liquid water the first thing we look for? So what I mean by this is when scientists consider the possibility of life on other planets, the first thing they look for is signs of liquid water. And most scientists are in agreement that liquid water is one of the prerequisites, one of the most essential things for life. Lots of experiments have been done where if you take simple or organic molecules, things like carbon and nitrogen and oxygen, those sorts of things, and basically combine them in the right kind of combinations in a liquid environment or add water, given a bit of energy, you start to get organic molecules forming, which we think are the sort of, the basic building blocks of living materials, living things. Interestingly, this question might seem quite arbitrary, but why does water do this? If you run a small stream of water from a tap and you charge up a comb, like in your hair or on a woolen jersey, and you bring it close to the stream of water, the stream of water is actually attracted towards the comb, and it bends around or towards it. You can actually deflect the stream of water towards the comb or some other sort of plastic rod. Interestingly, it doesn't actually matter whether the rod is positive or negative. The stream of water is always attracted towards the charged object. So this might seem like just something totally random and seem like it has very little purpose, or why is this important? But the answer to this question actually explains, or largely explains, the previous two. And I thought that's worth sort of noting, that sometimes in science, when we ponder some more obscure questions or try to explain small phenomenon, often the answers that we uncover can be applied to bigger picture and more important things. So answering this question might seem like a waste of time, but actually it yields information that's more fundamental to what's going on around us. So why does water do this? Well, it's got to do with the fact that there are polar covalent bonds in water. So this occurs when electrons are shared between two atoms, but they're not shared equally. If we look at a water molecule, basically we've got an oxygen with two hydrogens, and the electrons are shared, but they're shared much more closely to the oxygen. So sometimes one atom has a greater pull on electrons, and we call that pull electronegativity. So oxygen is far more electronegative than hydrogen. So although these electrons are being shared, that's a covalent bond, they're being pulled in much more closely to the oxygen. So this means that the oxygen end of the water molecule is actually slightly negative because the electrons spend more time or are closer to the oxygen molecule. And the hydrogens, which are essentially just a proton with its electron orbiting it, well, if the electrons that orbit that are shared more closely towards the oxygen, then essentially we have a proton that becomes a little bit more exposed on this end. So we have a slightly positive and a slightly negative end, and that's what this symbol is supposed to represent. So it's not quite the same as when we look at ions or ionic bonding, the pluses and minus. These atoms haven't gained or lost electrons, they're sharing them, but they're not quite being shared equally. Oxygen's getting the lion's share, so it's slightly negative, and the hydrogens aren't quite getting their share of those electrons, or they're pulled further away from them, so we get a slightly positive end on this side. So this actually explains why water deflects or is attracted towards a charged rod. The reason is that if the rod is negative, all the water molecules swivel around so that the positive side, the positive ends, face the charged object and are attracted towards it. If the object were positively charged, then all the negative ends, the oxygens, will swivel around to face that object, and they will be attracted towards. So because the water molecules are motile, whatever the charge is, the side of the molecule that's attracted to that charge will face that charge and essentially be drawn towards it. So it doesn't matter what charge the object is, because of the slightly positive and negative ends here, it means that the water molecule will be attracted towards it. So what's that got to do with life on Earth? Well, this creates a much stronger intermolecular bond between water molecules. What it means is that water molecules, when they're just hanging around by themselves, the positive ends, the hydrogens, will face or interact more frequently with the negative ends of a neighboring water molecule. So that attraction between the slightly positive end and the slightly negative end of water molecules means that there's a greater force of attraction between molecules. Now we've got to explain what the significance of that is. It's those intermolecular, those bonds between molecules that actually keep a substance solid or liquid at room temperature. So you'll remember in a solid, the particles are all touching and they're in a fixed pattern. So the force of attraction is strong enough to hold them in a certain position. Once it's heated enough that it melts into a liquid, the particles are still touching, but they can slide past each other. So in the case of the water molecules, that means for it to become liquid, we need enough energy that the pluses and minuses can slide past each other, and occasionally maybe not quite be matched up perfectly, the pluses and minuses, so not in the perfect kind of arrangement. But as a liquid, generally speaking, we're still going to have pluses and minuses, kind of that attraction holding them in place. So we've got enough energy that they can slide past each other and occasionally shift position slightly, but not strong enough that they can escape each other entirely. The force of attraction here between the slightly positive and negative ends is just too strong. It keeps them close enough together that they remain a liquid. So essentially these intermolecular bonds is what must be overcome in order to melt or to evaporate, for a substance to melt or evaporate. So that explains why water is liquid at room temperature, despite being such a small molecule. If you do chemistry and you look at alkanes, so things like methane, ethane, propane, all of those, getting longer kind of chains. Most of the small ones are gases at room temperature, and it's not till we get to sort of a 5-carbon chain that we start to get liquid at room temperature, and that's a much larger molecule. So oxygen, despite being such a small molecule, because of this unequal sharing of electrons, and because we've got a slight negative end and a slightly positive end, because it's polar, we get these strong intermolecular bonds. And those strong intermolecular bonds essentially help to hold the molecules together to keep it liquid at room temperature. So this particular type of bonding, with an unequal sharing between an oxygen, a highly electronegative atom, and a hydrogen atom, is called hydrogen bonding. It's just a particular type of polar bond, and a particularly strong one at that. So it just means that this is what kind of glues our water molecules together to keep them liquid at room temperature. So water is a polar solvent. Now what do we mean by that? Well, non-polar substances such as fats and oils will not dissolve in polar substances such as water. And that's basically, in a polar substance, those slight positive and negative charges create a force of attraction. And if something that is uncharged comes into the mix, there's essentially no attraction to those positive and negative terminals. So the slightly positive and negative of poles in the polar bond create an attractive force, but only between polar substances. Now that means that basically a non-polar substance can't disrupt those stronger polar bonds. So the attraction between those pluses and minuses. So I use this analogy here. It's a little bit mean, but we've got a group of polar substances here. There's a strong attractive force between them, strong bonds holding them together. And a non-polar substance cannot disrupt or get in between those polar bonds. So the polar bonds are those attraction, the slightly positive and negative force of attraction between those, and the non-polar substances can't kind of disrupt or get in between those bonds, so they end up being excluded. And what that means is that non-polar substances won't dissolve, won't get in between the polar substances. So water is an important solvent. So that means things that are charged or other things that are polar can easily dissolve into them. Non-polar substances like fats, we said, are insoluble. So if they're surrounded by water, they tend to be pushed kind of together because they'll bond with each other, but they can't disrupt the polar bonds. So here's an example. Here's some salt, sodium chloride, just your regular kind of salt. And what actually happens is when it gets into the water molecules can surround each of the ions. So here you can see a chlorine ion, and you can see the hydrogens, the slightly positive end of the water molecule, all swivel around and face the chlorine ion. Here we've got a sodium ion, a positive ion, and you can see the negative ends, all the oxygens can swivel around and face the sodium. So in this way they can surround the ions and actually separate them from each other. So this is why ionic substances, where we've got these charges, can actually dissolve into the water. So water serves as a really important substance in which important ions and other things can dissolve. It serves as a really important solvent in which all the chemical reactions that occur in our bodies, a place where they can actually occur. And if you think about it, those of you who do chemistry, almost all the reactions you do are taking place in water. When you've got a bottle of hydrochloric acid or a bottle of sodium thiosulfate or potassium iodide or whatever you're using, it's usually actually an ionic substance that's been dissolved, sometimes a covalent one, but it's usually a substance that's been dissolved in water. So 99% of what we actually use in chemistry is actually just water with a little bit of other stuff in it. This is what happens, hydrophobic interaction. Hydrophobic means water hating. If we have something like a fat, it actually it can't disrupt the bonds between the water. So you can see that here, which means that the water actually acts as a cage or a net around it. So that holds it together because the fatty substance here, the lipid, or the non-polar substance, can't disrupt or get in between those stronger bonds, those polar bonds that occur between the water molecules. Okay, so hydrogen bonding in water. It also explains why this hydrogen bonding, so the slightly negative end, the oxygens being attracted to the positive end, the hydrogen, also means that water molecules can actually line up in a regular arrangement. And this actually happens when water freezes, and we'll talk a bit more about that in a minute. So the hydrogen bond is a strong intermolecular bond that restricts the movement of the water molecules. So we said that before. Basically, these hydrogen bonds are what glue or help keep those water molecules together. Because they help keep the water molecules together, this means that water has a relatively high boiling point. It has a high specific heat capacity, a high surface tension, a high latent heat of vaporization. Now, what do some of these things mean? Well, a relatively high boiling point means it takes a high temperature before the water will actually start to boil, and that's because there's a stronger force holding the water molecules together. And when water boils, what we're doing is we're providing the energy to actually separate them. High specific heat capacity. Well, what is specific heat capacity? It's how much energy is required to change its temperature. So not only that, when we measure the temperature of a substance, we're actually measuring how fast the particles move. And in water, because there's a stronger force of attraction, a stronger glue holding the water molecules together, it takes more energy to get those water molecules moving. A high latent heat of vaporization. all right, is how much energy is required during a change in state from liquid to gas. So that's how much energy is required to actually pull those molecules, to finally pull those molecules apart. So in this case, during a state change, even though the temperature isn't going to increase, energy is needed to actually get it to change state. And again, the stronger the attraction between the molecules, the more energy is needed to essentially overcome or separate those molecules in order for it to change state. Now, surface tension, we'll talk a little bit more about that in a minute. So, alright, why is this so important? Well, basically, this helps to keep the temperature This helps to keep the temperature of large bodies of water more stable. So large bodies of water being things like lakes or oceans means that the temperature of these things is a lot more stable because it takes more energy than it would otherwise in order to change the temperature or to get that water to evaporate. So it means that that water is less likely to evaporate, or it takes a higher temperature, which means it stays liquid at room temperature. But it also means the energy doesn't fluctuate as much. It takes more energy to change the temperature of water than it would if we didn't have the hydrogen bonding. So hydrogen bonding is essential for water to essentially be able to sustain a more stable temperature. And so large bodies of waters like lakes and oceans have quite stable temperatures, and that's very important to the life within them. But I put here a large body of water. You can see here a large body of water. Our bodies are largely water too, and that property of water means that our body temperature stays more stable as well. Alright, because it takes a lot of energy to evaporate water, it also makes for an effective coolant. When we sweat, alright, a lot of energy goes into evaporating the sweat off our bodies, and that absorbing that energy is a way of losing heat energy to cool us down. So guys, here we spoke about this before. When water freezes, the hydrogen bonds cause the water molecules to align in a regular pattern. And this regular pattern results in gaps in between the water molecules. And that's why water is a very peculiar thing. Water is one of the few substances that when it freezes actually takes up more space. It expands. Most things get smaller because the molecules pack together more closely as they become solid. But water, because it lines up in a set pattern, and because there's these gaps in that pattern, it means it actually takes up slightly more space. Now that's actually really important because that regular arrangement fills a greater volume because of those gaps, which makes ice less dense. That's what makes ice float. Because ice is less dense, it floats, and that acts to actually insulate the water below. So if we're looking at an ocean or a lake, solid ice on top acts to insulate the water below and helps to prevent the entire body of water from freezing. So that's why often a lake, it's only the surface that's frozen, because essentially once the surface freezes, it helps to insulate and prevent the water beneath it from freezing as well. And again, that is really important for some living things that rely on liquid water that would otherwise die if they were frozen in ice. So high cohesion, this is the surface tension idea. So guys, there's a stronger bond between the water molecules, but at the surface, essentially, there's a greater number of bonds in this direction. They'll still bond with the ones down, but because they can't bond with anything above, there's a greater number of bonds in this direction between the water molecules, which means that there's kind of this elastic skin. There's a greater force of attraction between the molecules at the surface than there are within the water. And that gives, like I said, water this sort of slightly elastic skin, which even allows some insects like this one here to walk across the water walk across the surface of the water. So guys, lastly, I thought I'd just show this. This is a picture of the Earth, and it's been basically stripped of all its water, and you can see that over here to the side. So this is the size of the Earth. This is essentially all the water on Earth, and this tiny dot over here is basically all the fresh water on Earth. And that fresh water is so essential to so much of the life on the planet. that it is really actually probably a much more limited resource than we think of. We take for granted how much fresh water is around us. We look at a lake and it just seems like an endless supply of fresh water, but there's actually a very limited amount of fresh water on our planet, and so we should actually be treating some of those freshwater reserves with probably a bit more respect. So guys, it's those properties of water that make it, an environment, an important solvent for all those chemical reactions that are important for life to occur in, something that is liquid at room temperature, that is more stable across a wider range of temperatures, so that bonding between the water molecules keeps it liquid at room temperature. It means that the temperature doesn't increase as easily, so it has a more stable temperature. All those things are absolutely essential and crucial to life. So water really totally fundamental to life, and probably the most important of the biological molecules we'll cover. Okay, guys, that's basically it. So we'll leave it there, and we'll get on to the next one.